Everyone, welcome back, and today let's solve Leetcode problem 3349 titled Adjacent Increasing Subarrays Detection Part 1. So we're given an array nums of n integers and an integer k. We need to determine whether there exists two adjacent subarrays of length k such that both subarrays are strictly increasing. Specifically, we need to check if there are two subarrays that start at indices a and b, where a is less than b, and both subarrays from nums at a up until a plus k minus 1, and nums from index b up until b plus k minus 1 are strictly increasing, where the subarrays have to be adjacent, which means b is equal to a plus k just being the length of each subarray and being another one of our input integers. And we have to return true if it is possible to find two such subarrays and false otherwise within our input array nums. So in example 1, the reason why we have an output of true is because there are actually two adjacent subarrays of length k that are both strictly increasing, and that would be 789 and 234. Notice how they're completely adjacent to each other. The index here at 2 is equal to the index here at 7 plus 3, or plus k in other words, and they're both strictly increasing. 789 is increasing, and 234 is also increasing, and since we can find these two subarrays within this larger input array nums, we have an output of true. It is possible to get two kind of adjacent strictly increasing arrays of length k. For example 2, however, it is not possible, and so we have an output of false. Regardless of what kind of permutation or selection of adjacent arrays you choose that are all of length 5, you're never going to find any adjacent arrays that are both strictly increasing, and so for that reason, we have an output of false. So for the constraints here, we see that the length of the input array nums is always going to be between 2 and 100, and 2 times k is always going to be between 1 and the length of nums, kind of just validating our problem statement, and also telling us that any value itself in the input array nums is going to be between negative 1000 and 1000, kind of just confirming what the problem statement said, and just giving us some pretty straightforward constraints here. So I do actually have some code written out, which I don't want to have here for now, because we're going to get into how we actually solve this problem and the main kind of insight that we need to make to be able to solve it in the most efficient and elegant way possible. And that is the main kind of procedure here, if you will, to really understand is we just have to actually keep track of the two different cases to really worry about. And the two different cases really are, we could have a larger array of size k times 2, where that's completely strictly increasing, and just split that in half. Another way we could do this is if we had one strictly increasing subarray like 789, and then one that wasn't connected to it like 234. Notice how the entire thing here of all these 6 elements isn't particularly strictly increasing, but the two halves, 789 and 234, are increasing. That's an example of something kind of like our second case, where we still have two increasing subarrays that are adjacent, but they're not connected to form one larger increasing subarray like it was in the first case. And so how are we going to kind of structure our solution kind of around those two cases? Effectively, we're going to just traverse the array and keep track of the maximum strictly increasing segment as we iterate through the input. Basically, just the contiguous runs where each nums at index I is less than nums at index I plus 1, because that's the definition of an array to be increasing. Every element is less than the element that comes after it. Right? We're also going to at the same time keep track of the length of the current increasing run, which we'll just call something like current or cur, like we usually do in solutions, and the previous increasing run, right? And when a run ends, basically when we actually kind of have an invalid array or run, meaning it's no longer strictly increasing, so when a run ends, or we actually hit the end of the array, we're going to then calculate how many adjacent increasing subarrays of equal length we can actually extract from that specific run. Now, what are those two cases? Again, our first case is we can split the current run into two parts. Basically, the entire thing is strictly increasing, and we're just splitting it into two different parts of each length k to form our solution and return true. Or we can use the tail of the previous run and the head of the current run together, which would be kind of formed or computed using the minimum of previous and cur, like we see in example 1 from 789 and 234. Right, those are our two cases when we hit the end of a run as we iterate through the input. And we're also going to finally maintain a running maximum among these kind of different cases here, and if the maximum is greater than or equal to k, we know we can return true comfortably. right? And that's going to efficiently, eventually lead to a linear complexity, but we'll get more into how that works once we actually code up the solution. Let's go ahead and actually get into coding up the solution. So the first thing that I always like to do in, just general algorithmic problems and coding solutions is actually initialize all the different data structures, integers, and variables that I'm going to be working with in the solution. And in this case, that's quite straightforward. There's going to be three different variables, more specifically, three different integers. No data structures needed for this problem. That's going to be previous, that's going to be current, and that's going to be our maximum, or I'll just call it max, because max itself is a keyword in Python, so I'm just going to use mx. Now, previous is going to be initialized to 0, similar to current and mx, for now, that is. And the whole point of these three variables, like we talked about before, is the previous is simply going to keep track of the length of the previous strictly increasing segment, and the current is going to keep track, you guessed it, of our current strictly increasing segment. And this mx value here, technically representing max, is basically just the maximum possible k value that we can get for two adjacent runs, right? Now, as long as that maximum possible k value is at least k, we know we can do this and kind of fulfill the problem's requirements, because if it's at least k, we know that we can at least form two adjacent subarrays of length k, and so we will be able to comfortably return true, right? So once we've done that, now we can actually begin iterating over our input. But one last thing that I quickly like to do is, instead of going over for I in the range length of n, I usually call n my dimension of my input, or length of nums, just so it's easier to use when I'm iterating over the input and accessing the length of our input, right? So now let's actually begin iterating over our input, and quite straightforward, just a simple for loop here, for I in the range of n, basically just going through every single value, or more specifically index, in our input. And of course, since current is keeping track of our currently strictly increasing segment here for this specific run in this specific iteration, what I'm going to do is, for each iteration, because I'm including this next index in my current iteration, I have to always increase my current by 1, right? I'm essentially just including this next element, right? And once I do that, now I have to actually check if this run should end, meaning, is it one of the two cases? Do I hit the end of the array, or am I actually not fulfilling the strictly increasing kind of property anymore, meaning nums at I is no longer less than nums at I plus 1? And the way that I would kind of softwarely check that, or in terms of code, is if I is equal to the last index, meaning I is equal to n minus 1, let me format that better, or we've kind of broken that property of strictly increasing subsequences, nums at I, is now greater than or equal to nums at I plus 1. It's no longer strictly less than nums at I plus 1. That means we're either at the end of the array, or the next kind of element is not actually increasing anymore, and that is strictly increasing. That's why we have this equal to sign as well in this kind of non-validation check, right? And if this is the case, again, keep in mind there's two different ways or cases to form any adjacent runs. We can either, again, split the current into two equal parts, where we have current divided by 2, or current is simply the length of our current strictly increasing subsequence, or rather, not subsequence, but rather segment, or we can combine the tail of the previous run and the head of the current run, which would be kind of formulated by the minimum of previous and current. So we're going to update mx, right? Again, this is basically just maximum, and it's going to be the maximum value of either itself, of course, because we don't want to make it smaller. We are always trying to maximize it, or the two different cases that we're working with. That's either computed by current divided by 2, just splitting our current strictly increasing sequence into two different parts, each of length k, or it's going to be the minimum of the previous and the current, right? These are the two different ways we can actually compute this. Again, previous and current are just the lengths of our previous and current strictly increasing segments that we're working with that also have to be adjacent. That's all they are. And once we do that, we then have to actually update our kind of reset our variables from prev to be back to cur, because, of course, prev is now our new cur, or rather, cur is now our new prev, because we're going to be using this current strictly increasing segment as our new prev as we move on to future runs. And once we do that, we then have to update cur back to be 0, because we're resetting kind of our variable to start a new run, and so we have to reset our length, or the number of elements in our new run, back to be 0, right? That's really the whole point of that updating part of that problem, if you will. Now, once we do that, we're going to actually, at the end of the for loop here, return if we've actually kind of met the problem's requirements. We have to then compute all the different possible adjacent runs. Rather, once we've done that, we have to actually return if our maximum k value is valid. And so we can return mx being greater than or equal to, our k value, right? And if mx is greater than or equal to k value, that means we actually did find that we can make adjacent increasing subarrays of size k or more, and so we can immediately comfortably return true. Right, and again, to kind of reiterate what we were doing here, previous here, we're basically just moving its length into previous for the next comparison, and we're resetting curd to start counting from 0 in the next turn. And the key part here, and the reason how I got this, is effectively the two different cases. Back to that, we're either splitting the current in half, meaning if one long increasing run has the length of curve, that means it can contain two adjacent strictly increasing subarrays of length curve divided by 2. Or we can actually have something in the other case, meaning we can combine the previous and the current runs, meaning if one increasing run ends and another begins right after it, like we saw in example 1 of this problem, we can take one subarray from the tail and one subarray from the previous run, and then we can just combine that from the head of the new run. And the maximum adjacent length possible from those two would be the maximum, or rather the minimum, kind of the bottleneck of the previous and cur lengths, right? That's the maximum possible adjacent length that we can obtain from these two different possible subarrays that are strictly increasing. Right? And for example, to kind of give you an example of how the first case would work, if we had something like 1, 2, 3, 4, 5, 6, that entire thing is strictly increasing, and so we can split 1, 2, 3 to be 1 and 4, 5, 6 to be 1. That's basically the idea of how that would work. Or for something like the other case where we kind of use the previous and current tails, that would be something like 7, 8, 9 and 2, 3, 4. Right? They're not fully connected, but they're still two adjacent strictly increasing sequences from our input array nums. Right, so on a high level, again, how are we really solving this problem? What is the whole idea behind this? Effectively, we're really just iterating over our input regularly, quite straightforward, and as we do that, we're going to keep track of the current length of the current strictly increasing sequence, and also checking if we either break the property or we hit the end of the array, if we can actually maximize or update our maximum k value based on the two different cases that we formed. If either our current strictly increasing part of the array is long enough to have a larger k value, meaning cur divided by 2 is larger than the current mx value, or we can form our actual valid kind of sequences of at least length k using our previous and current subarrays that are both adjacent and strictly increasing as well. Right? And that brings us to the complexities of this problem here. For the runtime complexity, as we talked about, kind of glossed about in the explanation of this solution, it is linear, or in other words, big O of n. And the reason why is because we're really just using a single for loop or a single iteration to go through this input. And so we're going to go through every element exactly once, giving us a big O of n, or linear runtime complexity. And our memory or space complexity is actually constant because we're not actually using any extra data structures. We're only using a few integer variables like prev, current, and max, and so it is a big O of 1, or constant memory or space complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel, and without further ado, I will see you guys in the next video. Bye bye.